Hi, my name is Ali Shirsavar from Biricha Digital, and in this video we're going to talk about what is a LISN, how it works, and why we actually need one. So when you go to a testing house, the testing house will pass the power through a LISN before it gets to your device under test. A LISN stands for Line Impedance Stabilisation Network. It's a big tongue twister of a complicated phrase, but it's actually very, very simple. What the standard says is that you can't go to one testing house that has got a really nice clean supply with very low impedance and you pass the test, and your competitor goes to another testing house and perhaps the source impedance of that testing house is higher or it's more noisy and they fail the test. So effectively everybody has to take the same exam, and that is one of the jobs of the LISN. So what the LISN does, it will fix the impedance so that everybody tests their device under test according to a specified impedance which is in the standard. So it gives you a known impedance. Now it must let the power through into your device under test. So whatever it is that the LISN is doing, in addition to giving you a fixed impedance, it must allow DC or 50 Hz AC to get through without any problems. And then if the power supply of the testing house is noisy, you don't want the noise from the power supply to get into your device on the test and make you fail your test. So somehow the LISN is going to stop noise from outside to get into your device under test that is under measurement. And finally, your device under test is creating some noise and you want that to get through to the receiver or the spectrum analyzer so that you can decide whether you meet the standard or not. And of course, you also don't want the noise from your device under test to leak through to everybody else's power rails, right? So these are the four objectives of the LISN. Now let us see how it's going to do that, and you'll find that really it's just a couple of capacitors, couple of inductors and a couple of resistors that achieves all of these objectives. So the LISN that I'm going to draw is a CISPA16 LISN. There are other standards, but they're all very, very similar. So let's say you start, in our case, with a capacitor here. For CISPA16, that would be 1 microfarad. And then you've got an inductor. That would be 50 microhenries. And then you end up with another 0.1 microfarad. This is actually tied to a 1 kilo ohm resistor. I'll explain the function of this in a moment. And there we go. That will be your line, and this will be your return for a case of a DC source and device. Now if you've got AC, then this will become chassis. That's protective earth or chassis, and then you've got this mirrored on the opposite side for the neutral line. So that's neutral, and then you have another 1 microfarad capacitor, 1 microfarad, and then you have a 50 microhenry inductor. You have another 1 kilo ohm here, and then you have got a 0.1 microfarad capacitor. Now what happens is when you connect your spectrum analyzer, the spectrum analyzer's input impedance is 50 ohms. So there we go, that's 50 ohms, and you are looking at the noise here. So this is the place that you look at, and that is the spectrum analyzer. In order for this to be balanced, therefore, there needs to be another 50 ohm resistor here, 50 ohms. Now either you do this with a pre-compliance LISN like we do in a workshop with an external terminator, or the compliant LISNs have it internally with a switch, so they can switch this in and out, but this 50 ohm resistor is actually there. So let's have a look at what is happening. So when you look at it from this side, this is the power supply, power source of the testing house, and your device under test is being powered. Do I have another color? For a DC, from there to there. For AC, this will be your device under test. That will get connected to neutral, that would be line, and this will get connected to your chassis or protective earth. So first, you can see that the impedance has been fixed. This is sitting within. It's effectively a two-way filter. Now, the power has to get to the device under test without any problems, as we mentioned. For DC, which is only this bit, you can see that at DC values, this impedance here is huge, and therefore this goes out of picture. At DC, this is extremely small, so it becomes a short. Yeah, and then the power gets straight through here, and the return is there. Yeah? For AC, when you have line and neutral, again, for the power to get through, that's only 50 hertz. The impedance of this is big, so no current goes through there. So this goes out of picture, that goes out of picture. The impedance of these two at 50 hertz is very little, so power gets through to here. And then the impedance of these is also big. So as you can see, we have got a fixed impedance and the power gets through up to DC to 50 hertz. We don't have any problem. Then imagine that our source has got some noise, high frequency noise, right? So that is the noise that is trying to get in. At high frequencies, this is a short. So much of the noise will get diverted this way. At high frequencies, the impedance of that is huge. So much of the noise cannot get through. So again, bounces back and goes through there. So this is the path of lowest impedance for our noise. Therefore, it stops the noise from getting through to our device under test. And what we're going to measure is going to be the noise that is coming that way. Now, for neutral, exactly the same thing happens. If you have a noisy signal, high frequency noise going in there, it's going to get diverted and it's going to get returned and you don't get to see it. Let's now have a look at the noise that is coming from our device under test. So again, the noise is, let me take a different color. And high frequency noise now is trying to go this way. You will see that this now at high frequencies is very large, and that means that the noise can't go that way. 0.1 microfarad is small, so the noise gets diverted here. The 1 kilo ohm resistor here is literally there to stop you from blowing up your front end of your spectrum analyzer. If you imagine if that were not there, if you had any charge stored on this capacitor, as soon as you connected your spectrum analyzer, the charge in there would go straight in and it could damage your spectrum analyzer. And that's why we leave that there in order to discharge. This capacitor, 50 ohms in parallel with 1 kilo ohm, is around 50 ohms. So yes, we expect to have a 50 ohm impedance. Now, the noise cannot go that way. The noise will not really go through the 1K resistor, so the 0.1 microfarad is short to high frequency noise. It's going to go through there, it's going to go down through this 50 ohms, a voltage is going to appear around there, and of course that is what you see on the spectrum analyzer or the receiver if you're in a compliant test lab. And then the same thing applies to the neutral line. So if you have got any high frequency noise going this way, it's going to go there and it's going to get diverted through there, and you'll get to have a look at it there. So that is the function of the LISN. What we're going to do now is we are going to go to the lab and we're going to make a measurement and see how we get to see a signal that is coming through the LISN. Okay, so we are now here in the lab and we have discussed how the LISN functions. So now let's see it in real life. What I've got here is the LISN, the type that we use in our workshops. Usually you have your device under test here and the noise goes through, let's say, live and protective earth or neutral and protective earth. For now, I'm just using the Bode 100 to create a signal. So I've got a high frequency signal of around 15 megahertz, 13 dBm. So we've got another video which describes what we mean by dBms and so on. For now, 13 dBm translates to 1 volt RMS. So this is providing us with a signal just like a noise. So imagine that we've got a 15 megahertz noise of amplitude 1 volt RMS. It's going through here. And then it is going through the LISN and is coming out of the BNC connector. So the measurement of that is coming out of the BNC connector and is going to the spectrum analyzer. And it is also going through to the oscilloscope. A couple of things to note. Oscilloscope impedance is set to 1 mega ohms and the spectrum analyzer is 50 ohms. You're going to have that 50 ohms because the LISN expects to be connected to a 50 ohm load. Another thing to note is that quite a lot of LISNs, which have got a transient suppressor, as with this one, have got a 10 dB attenuator built in. So please don't forget to set that setting, otherwise your measurements will not be quite right. So if I go to the computer, the Bodhi 100 is sending the signal. You can see that I have set it to 13 dBm and 15 megahertz. So that is generating my signal. And now if I go and look at my spectrum analyzer, you will see that I have got a 15 megahertz 13 dBm signal. However, here I have set the reference offset to 10 dB because the LISN has got a 10 dB attenuator on it. Otherwise, your measurement will be off by 10 dB. Just like the previous video, if I change the units to microvolts, or in my case, I'm going to change it to volts so that we can see it, I have got around 1 volts according to the spectrum analyzer. If I look at the oscilloscope, you can see that I am reading around 1 volts. Again, remember that we have got a 10 dB attenuator. Now, 10 dB attenuator effectively translates to around 3 to 1 attenuator on your probe. So I haven't got a times 10 times 100. I've got effectively times 3. It's a user defined, so that my oscilloscope takes into account the 10 dB attenuator on this, and it gives me the right measurement. So if I slide back here, you will see that the oscilloscope is reading around 1 volts RMS with around 1.4 peak, which is exactly what we expect. And of course, that is the way the noise of your device under test gets passed to the spectrum analyzer for us to be able to see it. So we have got a presentation which is give you even more detail about how LISN works and so on. You can download that from the link below in the description. Thank you very much for listening, and hope to see you at one of our workshops.